Yeah, quieter every day.
Hey, everyone knows we're not doing answers today.
Or not.
No.
Stands up and goes away.
We're doing answers on Tuesday.
I still have to do the assignment. I've been procrastinating because of the convention
Oh, yeah.
and learning all of IT.
I think that's a lot. I took the Sage training the other day.
Yes. It's like all those like reading videos.
Yeah.
I did them all too. I hope you had less because yours is more on the approval side.
I still had to watch, I mean, the quiz, I think this is the same for everybody, and they're on the like a very obscure detail in the video, so.
It's so annoying.
Yeah.
It's like what exact law
Yeah,
in the California bylaws is it?
okay, mine wasn't like that, maybe mine was easier.
Mine
I only had 5 questions.
I have 5 questions, but one of them was the California bylaws and like the specific rule, we had to type in like 1020B.
Oh, really? Oh, okay, yeah, ours wasn't that annoying.
Because they went over that, like, oh, you can't request certain funding within school capita.
I see. Yeah, I mean, the only part of the video that applied to me was just like advisor approval. And so I just have to go in and just check it and then just tag you to say like it's done.
And you have to manually sign, you can't just do the type.
Yeah. If there's an issue, then I have to like at you, or I can just, email you like a normal person.
The funny thing is, I actually met our members today.
Okay,
I met half of them.
okay,
That means I met 6.
okay.
The other 12, yeah. And an event they want us to coordinate is where we can bring in alumni.
Yeah,
So Michael, I'm already talking to the sales leadership center, I'm trying to figure out who sends all the emails, send them an email so they can make, so when I make an event with them, they can announce it on the update.
perfect. Yeah,
I
that'd be
think
great.
we can get that through. I'm hoping to get in contact with UCI and Long Beach so we can do another bonfire.
Yeah, no, that'd be fun.
Hopefully either late October, first week of November, late October.
Mhm.
Just so the week after, 2 weeks after, right before. Either right before or right after, because we leave the second week, we're in third week, and then last week of November is Thanksgiving, right?
Yeah,
So on that third week, after like all the visits are done, we could do initiations, let's say that Friday or Saturday.
Yeah,
Well, that's Saturday.
I've been working on that with Dr. No, so I have all the data for the
So-
eligibility.
And I'm like, guys, he didn't consent, and like everyone's like. Title IX.
You're right.
And then someone was like, hey, let me take a photo, and just went like to the 0.5, like a top view, and I'm like, you didn't ask for his consent, and then he's like, oh my god, I'm so sorry. Title IX reports. That Karen guy could say so many. Staying on this side. Why? At this point, it's just for the view. Also, I like to see here.
Well, you can say you
This is your group
I
side.
think it too. No, on Tuesday.
Sorry, on Tuesday.
Oh, it's not on Tuesday. I just don't. You know what? Here you go. There's no one else to do for sure.
You just said you have Pepsi.
I do, but I also have that.
Oh, you're
Alright,
right.
want to get started. Alright, good afternoon, everyone. How's everyone doing?
Pretty okay.
No longer dying from the heat, so that's good. It's no longer Satan's butthole out there, it's livable. Okay, so today, no ANSYS today. So, our next ANSYS activity is planned for Tuesday. So, our schedule kind of got pushed back just because of the, because of the license server, beginning of the semester. So I kind of want to space it out because I don't want to give you guys another ANSYS activity while you're working on the other one. So remember, ANSYS activity 1 is due, this Saturday in 2 days. So make sure you get that in, and then we'll do our next ANSYS activity on. Okay. Okay, so the subject for today is boundary conditions. So we went over meshing on Tuesday, which I consider to be kind of the first big thing in FEA. Boundary conditions are the next one. All right, so we'll talk about what boundary conditions are, the different types of boundary conditions, what they represent, and so on. So, all right, any questions I can answer before we get started about the activity or whatever we talked about on Tuesday? Okay, all right, so let's go ahead and get started. All right, so the subject for today is boundary conditions. Okay. So in a nutshell, when you run an FEA simulation, you're running your simulation on a particular geometry. Right? But the way that we usually create our CAD models, our CAD geometry is kind of just floating in space, right? So we create a model of whatever part that we're analyzing, but we don't really model any of the environment that it's surrounded in. But in reality, when you create a part or when you engineer a part, design a part, it's going to be put within a greater environment. It's either going to be a component inside a bigger machine, bigger system, or it's going to be affixed to certain things in the environment. So the way that we model that, the way that we kind of incorporate the surrounding effects or the exterior effects is through the boundary condition. Because in most situations, or I would say in fact, all situations, the external environment or, the system that it's in, that's going to have a big impact on the, on the deformation or on the thermal response of your system. And so it's important that we incorporate that some way into our FEA simulation. Okay. So, that's how we think about boundary conditions, or that's how I think about boundary conditions just from a physical sense, right? So physically, in order to get a true prediction or a true simulation of, how your subject or how your part is going to behave in practice, you need to include the effects of the external environment. Boundary conditions also play a very important mathematical role as well. Because if you recall, FEA or just finite elements in general is just, a very, computational, sophisticated way of solving differential equations, okay? And so in order to get a complete solution to a differential equation, you need to apply boundary conditions on what we call the general solution. And this is not a new occurrence too, right? So you've already used boundary conditions in your previous math classes in 308. So let me just let's just do a very quick example to kind of remind you of kind of what this looks like. Okay, so let's consider a very simple kind of 1D differential equation. So let's consider differential equation d squared u x squared 2 3x squared. Okay. And so what we're interested in is we want to solve for the complete solution to this differential equation. But of course, in order to get a complete solution, we need to subject it to certain boundary conditions. So the first boundary condition that we're going to specify is that u of 0 is equal to 18. And then 2, say du dx, evaluated at x is equal to 10, is equal to -5. So those two conditions right there, those are boundary conditions, okay? And so what you're going to see is that we're not going to be able to completely solve this problem without using those boundary conditions. Okay, so let's go ahead and solve this first. So let's work on the governing equation first. Okay. So I chose this differential equation very intentionally, just because we can solve this just by straight up integrating. Okay, we're going to take the integral of both sides with respect to x. And so we take the integral on the left-hand side, we have a second order derivative. The integral is going to lower that order of the derivative by 1. On the left-hand side, we have du dx. And on the right-hand side, we have integral of 3x squared. Okay, so integral of 3x squared, that's just simply x cubed. But because we're doing indefinite integrals, we don't have any integration bound, we don't have any bounds on these integrals. This integration is only valid up to an arbitrary constant. So we need to make sure that we add that. We'll call that arbitrary constant C1. Where the value of C1 is 2b. Okay. So, but we're not done yet. So we want a solution for u of x. And so we need to integrate this one more time. We integrate this one more time, we get on the left-hand side, that integral is going to cancel out that derivative. Without my dx is there, so remember, we're taking the derivative with respect to x. So on the left-hand side, we have u of x. On the right-hand side, we have integral of x cubed plus c1. The integral of x cubed is 1/4, x to the 4. We have integral of a constant c1, and so integral of c1 is just going to be c1 times x. And then once again, since we're taking an indefinite integral, we have to add a second constant of integration here. We're going to add another constant c2. Okay. So what we have right here, this is our general solution. So it's a solution to our differential equation, but it's only valid up into these arbitrary constants. And so we're not going to have the full solution until we specify values for C1 and C2. All right. Any questions on how we got to this point here? Okay. And so of course, the way that we're going to specify these values is we're going to apply the boundary conditions. And so our boundary conditions are going to give us basically two mathematical equations that we're going to use to solve for these two unknown constants. Okay, so let me write down our boundary conditions again. Our boundary conditions, boundary condition 1 was u of 0 equal to 18. Our second boundary condition is du dx evaluated at x is equal to 5. Or excuse me, at x equal to 10. It's equal to -5. All right. So before we start plugging these in, let's look at the boundary conditions and let's kind of see what they kind of represent mathematically. Okay, so let's start with the first boundary condition. Let's kind of describe what this boundary condition is specifying with words. And so what this boundary condition is saying is that the value of the solution or the value of u when x is equal to 0 has to equal to 18. Okay? So what this is doing is that it's saying that when x is equal to 0, solution must have a value of 18. And then by that same token, we can kind of write a sentence to kind of describe the second boundary condition as well. And so this boundary condition, what that basically says is that at x is equal to 10. It's small semantics, but technically, saying at is more accurate than when, because x is a physical coordinate in this case, but I mean kind of the same. So at x is equal to 10, the derivative of the solution, right? So since this boundary condition is a condition on du dx, that's the derivative of the solution. At x equal to 10, the derivative of the solution must be -5. Okay. So the reason I kind of wrote those down, and so you write those down, you look at the equation, it's like it's obvious that that's what those equations mean, right? But let's go back to kind of our physical definition of the boundary conditions. So we come back up to the top here, and so we kind of rewind, 10 minutes ago in the past, right? What we said was that boundary conditions represent the effects of the external environment at the on the subject of our solution, okay? Or on the subject of our FEA simulation. Okay? If we assume, or if we define in this case, and we say that x is equal to 0 is the left bound of the domain. And then if we assume that x is equal to 10 is the right bound of the domain. What these boundary conditions are specifying is that they're specifying the behavior of the solution at the exteriors or at the ends of the domain. Okay? Okay. And so through this, you can kind of see the connection between kind of the physical interpretation of the boundary conditions and the mathematical interpretation. Okay? So they're one and the same. It's just, kind of two different ways to kind of describe it kind of in two. So underneath the hood, so when you're using ANSYS and you're applying the boundary conditions, ANSYS is basically doing exactly this. Well, not exactly this, the equations in ANSYS are a lot more complicated, but same idea, right? So when you solve the different, or when ANSYS solves the differential equations, it needs these boundary conditions to specify the full solution, which it then kind of displays for you in the columns. Okay, so let's go ahead and finish this up. So let's go ahead and apply these boundary conditions. Let's start with u of 0 is equal to 18. So let's go ahead and take our general solution here and plug in x is equal to 0. And so we plug in x is equal to 0 into our solution. We have 1/4, 0 raised to the 4th power, plus 1 times 0 plus c2 is equal to 18. All right. So in this case, we have a simple case, and so two of the terms here are just going to drop out because we're multiplying by 0. So we have a 1/4 times 0 raised to the 4th power, so that is just going to go away. And then we have c1 multiplied by 0, that's also just going to go away. And then all we're left with is just c2 is equal to 18. So straight away from applying that first boundary condition, we get the value of one of our parameters, or one of our constants very easy. Okay. And then our other boundary condition states that du dx evaluated at x equal to 10 is equal to -5. Let's remind ourselves what du dx is again, so du dx. Is equal to x cubed. Plus C1. All right, and so if we evaluate this at x is equal to 10, so we're gonna plug in x equal to 10 here. 10 cubed plus C1. That's gonna be equal to -5, okay? So let's evaluate x cubed or 10 cubed, so 10 cubed is 10 times 10 times 10, which is 1,000. Plus C1, equal to -5. We can solve this equation for C1. Get C1 equal to minus 1,000. So now that we have the values of both of our constants here, we can form our full solution. Our full solution in this case, u of x is equal to 1/4. X to the fourth minus 1,005 x plus 18. All right, any questions on this example here? All right, so that's it. So that example there is just to kind of illustrate to you kind of the purpose of boundary conditions. You know, we're not going to be solving in differential equations in this class. You know, it was just kind of a, you know, hopefully a refresher. Hopefully this all seems familiar to you. You know, just to kind of draw the connection between what we're doing in the ANSYS and what's happening kind of mathematically. Okay, so another way to kind of you know, look at the boundary conditions is to think of them as kind of like the active agents. Or another way, or you know, the way that I kind of like to think of that is that the boundary conditions are kind of the input into your FEA simulations. That might be kind of a strange way to think about it because, you know, technically there are a lot of inputs into the FEA simulation. So, you know, you have your CAD model, you have mesh settings, right? So all of those are technically inputs. But when you think about, you know, the FEA simulation as strictly just a boundary value problem, then the boundary conditions become the input to that problem, and that they cause a reaction, they cause a response from your domain, from your subject. I think I've mentioned this before, you know, when we were going over boundary value problems earlier in the semester, but you know, I just wanted to mention it again because you'll hear that terminology used, you know, mostly by kind of old timers, so people who've been doing either FEA for a long time or for, you know, applied mathematicians, and so, you know, it's not uncommon that you might be working together with those people out there in the professional world. So, you know, some people might use this terminology, and so, you know, I just want to make sure just that you're aware. Okay. So the next thing I want to talk about is to kind of talk about the different kinds of boundary conditions that there are and the types of effects that they have on our solution. And for our purposes, we're gonna focus on kind of a two class kind of specification here. And so we're gonna talk about two different types of boundary conditions. Okay, so the first type of boundary condition is what I call constraint type. So that's what we're going to talk about first. And then the second type of boundary condition is a load type. Mathematically, they have their differences in terms of how they affect the solution. But also, they're important. It's an important distinction because ANSYS kind of treats them a bit differently as well. All right. Any questions on anything so far? Okay, good. All right, so let's look at constraint type boundary conditions first. Another name for these types of boundary conditions is that these are often called Dirichlet boundary conditions. That's kind of the traditional name for them, and that's honestly kind of how I learned it when I was in school. Dirichlet obviously is the name of some long dead mathematician, and mathematically these boundary conditions are credited to him. But I like to call them constraint type boundary conditions because it's a little bit more descriptive in terms of how they affect our solution. Okay, so constraint type boundary conditions, they're given that, or the reason I kind of give them that name is because they force the solution to have a specified value at certain locations in your simulation. Another way that you can think about it is that you're constraining the solution to have a certain value, when you apply a constraint type. Okay. The key word here is that we're constraining the value of the primary solution variable. Right, remember we talked about in every type of physics that's allowed in ANSYS, there is a primary solution value that is solved first, right? So that's the direct solution to the differential equation, okay? And so a constraint type boundary condition is mostly concerned with the values of that primary solution group, okay? And in structures, remember the primary solution value is technically it's displacement, but the way that we kind of think about it is deformation. So let's look back at the example that we did earlier today, and let's see which of our boundary conditions is the constraint type boundary condition. And so if we look at our example earlier, the first thing that we have to ask ourselves is what is the primary solution variable? What's the first thing that we compute, from our solution? Okay. And so in our earlier example, our primary solution variable was u of x, okay? Or just to say kind of more simply, just u. Okay. That's the first thing that kind of pops out of our solution. We plug in values of x, that's the first thing that we can compute. Okay. And so that means that whatever boundary condition directly specifies the value of u, that's going to be a constraint type boundary condition. Okay. And so if we look at our boundary conditions, if we look at the first boundary condition that we had u of 0 is equal to 18. And so if you look at this boundary condition here, what we're saying is that when x is equal to 0, or at x is equal to 0, our solution has to take a certain value. Okay? So this forces the solution to take a value of 18 at x is equal to 0. And so that basically fits our description of a constraint type boundary condition, right? So, first of all, it acts on the primary solution variable, which is u, and second of all, it directly specifies its value. Okay, so this u of 0 is equal to 18 is kind of a classic example of a constraint type boundary condition. Okay. So what does a constraint type boundary condition look in ANSYS? So we've already used one. So we used one in activity 1. In fact, it's probably the most common constraint type boundary condition that you're going to use in this class. And so the constraint type boundary condition that we had in our first ANSYS activity was a fixed support. Okay. So we're going to use a fixed support in practically every single activity that we're going to do in this class. Okay. And so a fixed support is actually a very special type of constraint type boundary condition, because what it does is that it forces the displacement or it forces deformation to have a value of 0 on the areas that we specify. Practically, in every structural simulation, you need to have at least one fixed support somewhere in the model.
When there is no fixed support.
You can do it without a fixed support if you specify displacement boundary conditions, which we'll talk about soon. But kind of the easiest way to basically the reason you want to add a fixed support is that it prevents any rigid body motion or rigid body translation. And so the easiest way to do that is to apply a fixed support.
Thank you.
So, for the most of the time, when you're running ANSYS and you're doing ANSYS on the activities or the projects, first thing you should kind of ask yourself when you're applying the boundary conditions is, where is my fixed support? Where does it make the most sense to apply a fixed support? Okay, because without a fixed support, you could have some crazy things happen. So let's say that you have a simple beam. Normally for a beam, you have a pin support or some kind of fixed support on the beam, right? But let's say that this beam is not adequately constrained. Okay? And so let's say that on both ends of the beam, we have roller supports. Okay. So roller support will kind of constrain the beam in one direction, so it'll prevent the beam from kind of displacing up and down at the ends, okay? But it provides no constraint in the horizontal direction. And so if we were to apply a force, so let's say we were to apply a load like that, right? Then there's nothing that's preventing the beam from just, rolling down the street, right? And so instead of a beam, you just have a skateboard in this case. And so you need to have at least one, for the most or 99% of the time, it's going to be a fixed support. So you need to have a fixed support somewhere in your model. Otherwise you're going to have rigid body motion. The good news is that ANSYS is actually relatively smart. If ANSYS kind of detects ahead of time that your model is not adequately constrained, you're either going to have a very large degree motion, or if there's going to be any rigid body, translation or anything like that. ANSYS will actually warn you. So ANSYS will actually give you a warning and say, hey, this model is not adequately constrained. Large deformations may occur. Okay. And so if you haven't adequately constrained your model, then that can be like. And that's particularly useful, once you start getting into assemblies of parts. And so once we do activity 4, where you're gonna kind of have to, activity 4 is about something called shell and beam elements, but a big part of activity 4 is actually, taking a huge assembly of parts and properly fixing them to each other. And so if you don't do that properly, then ANSYS will actually give you a warning. But this is kind of really important to know is that, ANSYS will kind of naturally look for any kind of fixed support or displacement support in your model before it allows you to run a simulation. All right, so just kind of for your information, we're talking a lot about displacement deformation just because, we're again mostly going to be working with structural simulations. But if you were to run a thermal simulation, then the primary solution variable in that case is temperature. And so any kind of boundary condition that specifies the temperature at a certain location, that is your constraint type boundary condition. All right, any questions on constraint type boundary conditions? Okay. All right, so let's go ahead and move on. So the next type of boundary condition that we're going to talk about is load type boundary conditions. Okay. So while constraint type boundary conditions, directly specify the values of the solution. The way low type boundary conditions is that eventually they are going to specify the values of the primary solution variable. It just kind of does that in an indirect way. So low type boundary conditions are basically every other type of boundary condition out there that has an indirect effect on the primary solution variable. And of course, I'm using the term indirect there a little bit loosely, right? By indirect, what I mean is that it's, kind of the opposite of the constraint type boundary conditions, where the constraint type is very simple, right? When you have a constraint type boundary condition, you know exactly what the primary solution variable is gonna be at that location, right? And so if you have a fixed support, you know the deformation is gonna be 0. Usually by indirect boundary condition, usually what I mean by that is that, in order to kind of predict the effect on our primary solution variable, we have to kind of solve additional equations. A lot of times, it requires a solution of governing equations to find the real effect. All right. So, just by process of elimination, if you think back to the example that we did at the beginning of class today, right? We had that boundary condition that was based on the derivative of our solution. We had du dx, evaluated that, x is equal to 10. Okay. Right. And so this does count as a boundary condition, obviously it is, right? But just by looking at this, by itself, we can't really tell right away what the value of u is at x equal to 10. Because we've already kind of established that x is equal to 10 is one of the boundaries or one of the exterior or the bounds of our domain, right? And we're interested in finding out what u of 10 is, but that's not immediately clear from this boundary condition, right? And so in order to find out what the value of the solution is at x is equal to 10, we need to evaluate this boundary condition, we need to plug it back into our full solution, and then from the full solution, we evaluate that at x equal to 10, and then that determines what our solution is there. Okay. And so that's what I mean by, these low type boundary conditions provide an indirect effect on our primary solution variable. That seems relatively clear. So low type boundary conditions are very plentiful. So, the majority of boundary conditions that you're going to find in ANSYS kind of belongs to this low type. So the ones that we're going to use the most in ANSYS are probably force boundary conditions and pressure boundary conditions. Another thing that you can specify, a little bit more uncommon, but also important as well. You can directly specify a stress type boundary condition. Okay. Maybe you're simulating a situation where you have shearing stress applied to your model. That's probably the most common case. And so you can apply that shearing stress as a stress type boundary condition. Okay. All of these kind of fall under the umbrella of a load type boundary condition. Because again, of course, these boundary conditions are going to have an effect on the deformation of your model, right? You apply a force to a structure, it's gonna deform in a certain way. It does so in kind of an indirect manner. Okay, so you have to solve the equations first, before you find out kind of what the solution variables is. Okay. So strictly speaking, even though load type boundary conditions are very common, and in fact, we're going to use them a lot. Strictly speaking, they're not a requirement on an FEA simulation the way that constraint type boundary conditions are. So while you can't run a simulation without a constraint type boundary condition, it is possible to run a simulation without a load type. Okay. And one way that you can do it is by specifying a displacement type boundary condition. So if we look back at our example, right? So let's change the second boundary condition to another constraint type boundary condition. And so instead of du dx at x is equal to 10, 5, okay, let's change it to. Okay, so if we change it to another constraint type boundary condition, what we're saying is that we're going to directly specify the value of u at x is equal to 10. Okay. And so if we change that, so we say instead we say u of 10 is equal to, I don't know, let's say it's equal to 100. You can take this result or take this boundary condition along with the original constraint type. You can take these two boundary conditions and you can get a valid, full solution for this. Okay. Kind of the ANSYS equivalent of this is that if you specify two kind of displacement type boundary conditions on two parts of the model. So let's say that we have our beam here. So let's say that we fix the beam on the left-hand side. Okay. Right, so we have our fixed support, so that's kind of our requirement. And then on the other side of the beam, let's say that we're going to pull on it, and we're going to pull until it deforms by a fixed amount. And so this X naught here, that is the, well, let me call it, use X for now. Let me call this L naught. So let's say we're gonna pull on the beam until it deforms by an amount L naught, okay? So we have a specified deformation on the right side of the beam. You can solve this, and so if you solve this in ANSYS, you're gonna get a valid solution, right? And what you're gonna see is that, in this case, it's just gonna be a linear kind of change, and so it's gonna go from 0 deformation on the left, it's going to change linearly until it reaches a maximum L naught on the right. But this is perfectly valid, so you can have a simulation with all constraint type boundary conditions, and you're gonna be just fine. Okay? It may not be the most interesting simulation results in the world, well, it kind of depends. If you're in 2D and 3D, it may look interesting, but you can still do this. What you can't do. What you can't do is that you can't have all low type boundary conditions. And so again, thinking back to our original example, right? So in our original example, we had our original constraint type boundary condition of u of 0 is equal to 18, right? If we were to replace this, instead we replace it with du dx at 0, let's just say that this is equal to 10. If we have this boundary condition together with our original second boundary condition, right? So if those were the two boundary conditions for our system, you'll be able to find out very quickly that you're not going to be able to find a valid solution with these combination of boundary conditions. I'm not going to go through the whole math just in the interest of time, but I'll give you kind of a sneak preview of what's going to happen. And so if you were to try to solve that equation with those two boundary conditions there, you will be unable to specify the value of C2. Not only can you not specify the value of C2, but the value of C1 will be over constrained as well. So you have kind of, too many equations for, too many equations for the amount of unknowns that you. And of course, the physical reason of why you can't have all force boundary conditions is, we've talked about it before. So, you're just going to get rigid body motion. Okay. There are exceptions to this, and so if you have a perfectly symmetric case, so you can imagine that when you have a block that's in the air and you're applying equal and opposite forces on both sides, and so if the force type boundary conditions are enough such that they naturally kind of equilibrate on their own, then technically you can run this in ANSYS. But that's kind of more of a parlor trick more than anything practical, because for a simple case, like if you're simulating the Hulk smashing a brick, yeah, you can put two equal forces against each other. But if you have kind of a very complex kind of geometry with curvature and all that stuff, it's very difficult to apply the forces in an exact way so that they all kind of cancel out, especially when you think about rotations and moments and things like that. So for the most part, it's easiest just to apply a fixed boundary condition, and then any load that kind of makes sense. All right, any questions on this? Okay. So last thing I want to talk about today is some, I would say, I call them kind of practical considerations for boundary conditions. So, for the majority of class, you're gonna take the role of kind of like a user of ANSYS, right? And so, you're not really gonna be thinking about the mathematics behind the equations on the boundary conditions. You just want to apply them to your model. So kind of taking what we kind of talked about today, count, as well as some other kind of practical tips, let's kind of list some guidelines here. Because the bottom line is that boundary conditions are a really important part of your finite element simulation, right? And of course, I'm going to say that about every aspect that we're going to talk about: meshing, boundary conditions, material properties, the geometry itself, right? All of these are extremely important. And so you can't really have a valid finite element simulation unless they're all kind of working together. So let's kind of talk about why boundary conditions are important. Okay, so the most important consideration, or the most important thing that you need to think about when you're applying boundary conditions, is that you need to make sure that the boundary conditions are physically consistent with what you want to model, with what you want to simulate. ANSYS really does you a great service in this case because you don't have to apply the boundary conditions in a mathematical way, right? So you don't have to take your physical force or pressure and then kind of come up with a mathematical expression for it. ANSYS does it for you. The only thing you have to do is just kind of interpret your situation and apply the proper forces and pressures and make sure they're in the right directions and make sure that you're fixed in the right place. All this has to be consistent with the physical situation that you want to model. Okay? Because remember, the whole reason you're running FEA is you want to simulate or you want to predict, what's going to physically happen to your part or to your system when you expose it to these conditions. And so that may seem like a very obvious point, right? And so, you're not going to get an accurate solution unless your boundary conditions are accurate. But boundary conditions is kind of one of those things that, besides kind of the hard rules that we talked about in terms of, making sure you have a constraint, making sure that, that there's enough loads there, right? So those are things that ANSYS will warn you about, right? So everything that we talked about before, but making sure that your boundary conditions are physically consistent with the real life situation. ANSYS has no idea what the real life situation that what you're trying to model is, right? And so as long as your boundary conditions meet the minimum requirements, then ANSYS will give you a result. Okay. But that's dangerous because then, then it's not up to ANSYS to tell you, whether your simulation is wrong or inaccurate. It's going to be up to you, the engineer. Okay. So that's something that you kind of always have to kind of be thinking about is, when you're applying a force, think about, what's the origin of this force? How is it being applied? What direction is it being applied? So you need to make this check because ANSYS is not going to do this for you. if you apply, oops. Oh, okay. There we go, okay. All right, so if you apply the wrong boundary conditions, so let's say that you apply boundary conditions that are not physically consistent with your real life case, right? Your simulation results are gonna be completely wrong, right? And you won't, and you know, in the worst case, you're not gonna know until you actually build the structure and then it all kind of falls apart. Okay? And you know, just based on kind of my experience, the biggest source of human error in setting up an FEA simulation, and that's not only, you know, for this class, but you know, this kind of what I see just in general from, you know, from people setting up simulations in industry to research people, right? The biggest source of human error is setting up the boundary conditions. In fact, you know, yesterday evening, you know, I was reviewing a manuscript of a paper that was sent to a journal, right? And then kind of the biggest question that, I mean, it was a high quality paper in general, you know, they did a great job, but the biggest questions that I had, you know, for the authors was, you know, how they set up the boundary conditions, because they weren't 100% clear on that in their manuscript. So, you know, that was the main thing I asked them to kind of clarify is, you know, make sure that you kind of fully specify your boundary conditions. And sometimes, you know, it's not easy to kind of, you know, determine what the right boundary conditions are. So, you know, and I think you're not really going to get an appreciation for that until you do your final projects, because, you know, a lot of the activities that we're going to do, a lot of the even the midterm project, you know, I'm going to be giving you guys the geometry for that. Those are very kind of clean cut, kind of very obvious what the boundary conditions should be. You know, but if you're analyzing a certain component that's part of a larger structure, where that larger structure itself is going to be forming and kind of doing all this crazy stuff, right? So for instance, you know, if you're you know, just an example from last year, right? So let's say that you're simulating kind of the robotic arm of the rover, right? The boundary conditions are not that straightforward enough, because, you know, the robotic arm is attached to the rest of the chassis, and that's, you know, and that's going to be moving, that's going to be, you know, the force is going to be changing with time on that as well. It's going to depend on the position. So, you know, it's not the easiest thing, and oftentimes, you know, you may have to go through certain iterations in order to get the boundary conditions. So, you know, I'm spending a lot of time on this because, you know, I really want to stress that, you know, what you apply for the boundary conditions, how you apply it is really, really important. Okay. And it's going to be the number one question that I'm going to ask you, you know, once you get around to your projects. You know, what are your boundary conditions? How are you specifying them? You know, why did you specify them in this way? And, you know, why does this make sense to you? All right, any questions on this first point? Okay, good. Okay, number two. Number two is a little bit more straightforward, right? So boundary conditions can be applied on any exterior facet of your geometry, right? And so that means you can apply a boundary condition on a surface, you can apply it on a line, or you can apply it on a point. Basically, any exterior part of your model you can apply boundary conditions. But when you have a choice, right? So when you have a choice of applying the boundary condition on a surface, an edge, or a point, generally you want to apply the boundary condition on as large of a surface as possible. So surfaces are more preferable to edges, and edges are more preferable to points. Sometimes it makes sense, kind of given the type of boundary condition or the force. Sometimes it makes the most sense to apply it on an edge relative to a surface, right? Maybe it is, something that's just contacting your part right on an edge, or maybe it's something that's contacting your part right on a point. Okay. So sometimes physically it makes sense to apply things on points and edges, but if you have a choice, right? Generally, you want to apply the boundary condition on as wide a surface or as big a surface as possible. Okay. And the reason for this is that it leads to kind of more stable solutions. Right. Sometimes what can happen is that if you apply a very large force at a point, it can cause your simulation to do kind of weird, unstable things. Number 3. Okay. Number 3, it's not required to apply a boundary condition on every exterior surface of your model. Okay. What ANSYS does, and actually, pretty much all finite element softwares do this as well, is that if you don't specify a boundary condition on a certain surface, it will apply a default condition on that surface. So by default, ANSYS kind of applies a default condition. So you don't have to worry about applying a condition on every surface. Okay. What I usually tell people is that you should only apply a boundary condition on a surface if there's a non-trivial condition. Okay. And so there's actually a fixed support that there's actually a force. And if you're curious what the default condition is, it is, technically you can apply the default condition yourself. It's not really a mystery. And so the default condition is a zero stress boundary condition. Basically, in other words, from a structural point of view, right? A zero stress boundary condition means that that surface is contacting air, right? Or yes, if you want to be technical, yes, air is applying atmospheric pressure on the model at that point. But atmospheric pressure is applying it on every surface, right? And so, relatively speaking, that there's zero stress, zero pressure. Which makes sense, right? So if I didn't mention anything at all, I think that's what most people would kind of assume, is that when you don't put a boundary condition on a certain surface. Okay, and so the last tip. The last tip is that it is possible to apply multiple boundary conditions on the same surface. That is possible to do. For the most part, you're only going to be really doing this in the case where you're applying multiple loads, and oftentimes it's because those loads are applied in different directions. Okay? So I think we'll do something like that. I think it's activity 6. One of the last ones that we're going to do in this class. So we're going to see multiple loads. It's not, it makes a lot of sense, but just know that you're not limited to just one boundary condition per surface. Okay. But you want to be careful a little bit if you're applying a load on the same surface as a constraint. So if you're applying a load on the same surface as a constraint, then the constraint is basically going to overwrite the load. So the load is going to have basically no effect on your. And so physically, it's very easy to kind of demonstrate this. Let's look at our beam again. Right? So let's say that we have a simply supported beam. So we have a fixed support or a pin support on the left-hand side, and on the right-hand side, we have a roller. Okay. If you were to apply a tensile load on the right side of this beam, right, you're going to get an interesting solution, right? Because you're able to pull the beam and the roller support's not going to impede that, and you're able to kind of stretch the beam out completely. Okay. If you were to apply a load on the left-hand side, so let's say that you apply a compressive load on the left-hand side, right? This load is going to have no effect on the beam itself, right? You may see, there might be a little bit of hangover here where, the part of the beam that's not connected to the support, that part might be compressed. But the fact that you have a fixed support right here, okay, this fixed support kind of acts like a wall. And so the effect of that force is not going to extend past that wall. So the entire right side of the beam right here is going to be completely. And so, the same thing can happen in ANSYS as well. So if you apply a load at the same location as constraint, then it'll basically almost be like that load isn't there. Okay. For the most part, if you're kind of careful when you're kind of thinking about your simulation, this doesn't really happen. But just know that ANSYS is also not going to stop you. And so if you apply a load at the same place as constraint, ANSYS will just be like, cool. that does nothing, and so, just kind of be aware. It's kind of more common, you kind of see it more commonly in cases where you have a lot of different loads, so say you have a complex geometry. And you have lots of loads going everywhere and kind of change things mid simulation. And so you just want to be careful that, you don't have a situation. All right, any final questions before we wrap it up for today?
So question, when it comes to answers, like the program itself, you know how CAD tells you like if all sides are defined, right?
Yeah.
Does answers tell you like how many rows do you have in a certain area or the type of stuff?
Not that I'm aware of, and so ANSYS will kind of show you visually in terms of like on the figure itself. But it doesn't kind of give you a summary in terms of how many loads or constraints. You kind of just kind of count those from the. Yeah, usually there's not that many that it's hard to kind of visualize. Usually you kind of just count it from the list. But maybe for more complex ones, they may have a little bit, but I haven't seen it. So. All right, so that's all we had time for today. So thank you guys for coming today. Remember, ANSYS 51 is due on Saturday night, so make sure you put that in. So hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys next week.
Just a question, when you scroll up to the list. Yeah.
Hey, everybody go. Everybody go. What we gonna get some poke? Some poke? Sheesh.
Okay. I mean, I follow these pretty close. Just look up the-
Oh, really? Thank you.
I feel so fun. She's right there. Not a lot of people are there. Yeah, like,
Yeah, I have it in my log. Did you go?
Yeah, I got one, but it's an older model.
I think we got a 20. Yeah, I heard like that much of it. Yeah, it's his old.
Already?
Yeah, but I got it, raised Kevin.
Oh, Kevin?
Kevin had it, I asked him if he could sell it to me or give it to me, and he just gave it to me, so.